Welcome back, Rockridge High School. We are talking about Algebra 2 on a lesson regarding simplifying and rationalizing radicals. This is a bit of a continuation of our last lesson on simplifying radicals. It's a lot more practice and a bunch more steps in our simplifying. So we're going to crank it up a notch a little bit in our learning today. Now, I can't stress enough how important it is to quickly recognize the numbers that go into this table, right? I'm not going to fill in this complete table here for you. You can do that. But knowing that 3 squared is 9, and finding those nines, those factors of numbers that are nines is important, or that the cube of 3, 27, the cube root of 27 is 3, is so important to getting through these problems quickly. So the sooner you can recognize 27s and 64s and 125s, the cube root of 125 is 5, the sooner you can see those, the better these works are going to go for you. Okay, so just want to emphasize that. So I would try to fill this in on your own without using a calculator to see how many you know and try to memorize the rest of them. It will make these go so much faster. Alright, so let's take a look at what we have here. So more practice on simplifying radicals. We'll do that first. Simplifying these radicals, we need to look for, in this case, this is a regular old square root, so we need to look for things that are perfect squares. I'm going to make some notes to myself. I'm going to make a note that 36, I'm going to think of this 36 as 6 squared. I like to see things that are to the 2 power, because when I take the square root of them, I just grab the bases, okay? So that's why I do this. And I want to think of w to the 5th as w squared times w squared times w. Now, I'm going to go ahead and take this action. Again, the orange is just my note to self. Now I'm going to take this square root action. The square root of 6 squared is 6. The square root of w squared is w. The square root of w squared is w, and then since this last one is just a regular old w, you get left behind as the trash. Clean this up for me. 6w squared times the square root of w. And again, as we discussed last time, if you are a fraction person and you think of 5 divided by 2 is 2 with a 1 left over, that's completely fine. That is completely fine if you like to do that. I will continue, however, with the visuals, the visual breakout. 5th root of 64. Did we see something to the 5th power is 64 on our chart? No, we didn't. But there was a factor of 64 that was. 64 can be broken down into 32 times 2. The reason I care about that is the fact that 32 is 2 to the 5th. Okay? The fact that 64 can be broken into 32 and 2, or 2 to the 5th and 2, is important. So that's my note to self. Now I'm going to take the 5th root of things. I'm going to take the 5th root of 2 to the 5th, that's just 2, and leave behind the 5th root of 2, the leftover. Okay? Let's look at example 3. Square root land again, so not 5th root, square root land. What can I break 18 down into? Because I know the square root of 18 is nothing pretty. But I'm immediately thinking, wait a second, there's a 9 times 2 in there. There's a 3 squared times 2. Within the m cubed, there's an m squared times m. So I'm going to grab what I can. The square root of 3 squared is 3. 2, I'll see you in a minute. The square root of m squared is m. I'll see you in a minute. And the leave behind are the 2 and the m. Number 4. I need to be recognizing perfect cubes because I need to take the cube roots of things. So I immediately recognize that 8 is 2 to the 3rd power, 2 cubed. R is already set up nicely for me. It's an r to the 3. I'm going to take the cube root of r to the 3rd and get r out of it. S, not so much, so let's break this into things that are useful. S to the third is useful times S squared, right? S to the third times S squared is S to the fifth. You're going to be left behind. I'm going to take the cube root of S cubed and make it an S, but this S squared is going to have to be left behind. Now into the T's. I'm going to break that into T to the third times T to the third. I'm going to get as many of these third powers out as possible. T to the third. So that's 3 plus 3 plus 3, that's 9, and then I have just one T left over, T to the 1. Now that I've broken that out in my own head, or on this little paper here, I'm going to take the cube roots of things that I can. So the cube root of 2 cubed is 2. The cube root of R cubed is R. The cube root of S cubed is S. The cube root of S squared, well, you're not big enough. You're going to have to be left behind. The cube root of T cubed is T. The cube root of T cubed is T. The cube root of T cubed is T. T, you don't have a 3 there, you're left behind. Times the cube root of the leave behinds. Let's scan for leave behinds. I've got an S squared left behind and a T left behind. Final step, let's clean this up. 2 R S T to the third times the cube root of S squared T. Please don't forget to put this little 3 on this shelf here. Otherwise, you're telling me that you're taking the square root of this. That's not what you're doing. You're taking the cube root of these leftovers. So that is your simplified radical. Let's go to example 5. Example 5, I'm looking for fourth roots. Fourth roots. So what lives within 48 that is something to the fourth power? The fourth power. Hopefully you came up with 16 and 3. 16 is 2 to the fourth power times 3. So 16 times 3 is 48, and I was looking for that 2 to the fourth power because I'm taking the fourth root of it. Okay, so again, I can't stress enough, having that table memorized is super important to making these steps go quicker. All right, enough of that. A to the 12th. Let's break that into things that are to the fourth power. So I've got an A to the fourth times an A to the fourth times an A to the fourth with no leftover A's, so all of you are coming out. And then the B to the 10th, let's break that into B to the fourth times B to the fourth times B squared. Let's take what we can and leave behind what we have to. So this is our orange note to self. Now let's take this fourth root. The fourth root of 2 to the fourth is 2. 3, you're going to be left behind. The fourth root of A to the fourth is A. The fourth root of A to the fourth is A. The fourth root of A to the fourth is A. The fourth root of B to the fourth is B. The fourth root of B to the fourth is B. You get left behind. We have the fourth root of the leave behinds. That's 3B squared. Do not forget this little 4 on this little shelf. Clean this up. 2 A to the third B squared times the fourth root of 3B squared. That is the simplified version of example number 5. Number 6. Number 6 is interesting. Sitting here by itself, we don't have a breakout like this to do that's quite as clear. We could certainly look up here for some breakouts, and we could pull an X out, so that's certainly an option. We could start pulling things out. What I would like to pose to you is that we can rewrite this. Since this is the same square root, we can rewrite this as the square root of 75x cubed over 3x squared. That's incredibly useful. Breaking things out would have been fine. We would get to the same place. But if you can see that this action can be taken in here, and that we can reduce this fraction first before taking this radical action, you should take advantage of that and make things easier on yourself. So let's reduce this fraction. 75 divided by 3, that's 25. X to the third divided by x squared, you should know that that's the 3 power minus the 2 power, so that's just x. At this point, you should see that if you take the square root of 25, you'll get 5. And that this x needs to be left behind because he's not to the 2 power. Okay? So 5 times the square root of x is that simplified down. Take advantage of whatever you can when you're reducing these. Now in number 7, it would have been real nice if this was 8 over 81, but it's not. If it was 8 over 80, it would have been great because we could have reduced that to 1 over 10, but it's not. It's 8 over 81. So let's see if we can use something else to our advantage here. Last time, we had things separated into square root divided by square root, and we consolidated them. Let's see if we go in the reverse direction, if that might help us out. So instead of having this whole fraction be here, let's see if we can take them separately. 4th root of 8 over 4th root of 81. Does that help? Does that help? It absolutely does. And again, hopefully you've got that table rummaging around in your brain. You should immediately see that the 4th root of 81 is 3. 3 times 3 times 3 times 3 is 81. So the 4th root of 81 is 3. And there's really not much else we can do. We can't simplify this down. This 8 can be thought of as 2 to the 3rd, but not 2 to the 4th. So we're kind of stuck with it. But the fact that we've simplified this denominator and gotten the radical out of the denominator reduces this enough for us. Okay, so look for everything you possibly can. All right, number 8, let me explain to you how we can multiply two binomials that have radicals as part of them, okay? So let's take a look here. Just like we did before, let's FOIL. First times first, outer times outer, inner times inner, and last times last. Let's do that here and see how it plays out, because you will need to be able to do this, exercise this skill. So first times first, 2 times 3 is 6. Outer times outer is negative 2 square root of 7. The 2 is being multiplied by an invisible little negative 1 out here. And the square root of 7 doesn't have another square root over here. So the 2 stays on the outside and the 7 stays on the inside. So that's how that works. So that was outer times outer. Inner times inner. The 3 doesn't have a radical, the 5 does. So let's turn that into 3 times the square root of 5. That's how that works. And then last times last, we've got a plus and a minus. So we've got minus. And then since these are both under the square root, you make that the square root of 35. Okay, so make sure you are confident in that skill. There are no radicals to combine here. Okay, the square root of 7 cannot, these negative 2 square roots of 7 cannot be combined with 3 square roots of 5, and they cannot be combined with a negative 1 square root of 35. Okay, you cannot combine these unless they are exactly the same. If this was negative 2 square roots of 7 and this was positive 3 square roots of 7, you could combine them, but they are not. They are not the same. So we are finished here. That is this multiplied by this. Example 9, again, use whatever you can to your advantage. Okay, these are currently separated into the square root of 48x squared divided by square root of 16. You can certainly make this into a 4 and pull out perfect squares, but hopefully you immediately recognized that if you were to put this all under the square root symbol and reduce the fraction inside it, it would make things go quicker. If you were to recognize that 16 goes into 48 3 times, this would go quicker for you. Again, you certainly can go ahead and pull what you can outside and reduce down later, but reducing within the fraction and then taking the square root will go quicker for you. Don't forget, if you take the square root of x squared, you need to indicate that's the absolute value of x times the square root of 3. Remember that lesson? So that is that simplified down. If you had done these separately and then reduced the fractions, you'll still get to the same place. All right, let's take a look at example 10. Now let's not forget that this 2 is waiting to be multiplied by whatever comes out of here, and this 3 is waiting to be multiplied by whatever comes out of here. We are looking at cube roots, so we need to look for things to the 3 power. So what is something to the 3 power that's a factor of 16? Again, you should have that table running through your head and immediately say, there is a 2 to the 3rd power in there. There's an 8 in there. 8 times 2 is 16. And within the x to the 5th is an x to the 3rd times x squared, because I want to pull this x to the 3rd out and I'm going to have to leave the x squared behind. So that's my little thought on that one. My thought on this one, if I look at the 54, have that table in mind. Is there a factor of 54 that is something to the 3rd power? Absolutely there is. 27 times 2 is 54. So 3 to the 3rd power, or 27, times 2 is the breakout of 54. That's the useful breakout. Start recognizing these numbers for yourself. Let me break out x to the 8th. I've got an x to the 3rd times an x to the 3rd times an x squared. All right, let's pull out what we can. Now, do not forget that this 2 is out here waiting to be multiplied by whoever comes outside. So this 2 is out here already. Now let's take our cube roots of our notes. Cube root of 2 cubed is 2. This is nothing to the 3rd power, so it stays behind. Cube root of x to the 3rd is x. This is nothing to the 3rd, so it stays behind. So I've got a cube root of 2x squared left behind. Plus, this 3 is waiting to be multiplied by whoever comes outside. The cube root of 3 to the 3rd is 3. 2, you're nothing to the 3rd power, so you stay behind. Cube root of x to the 3rd is x. Cube root of x to the 3rd is x. You're nothing to the 3rd power, so you stay behind. So leave behind, so the cube root of 2x squared. Clean a little bit of this up, so 2 times 2 is 4x times the cube root of 2x squared. Plus 3 times 3 is 9, x squared times the cube root of 2x squared. That's how that works. Do not forget that these numbers are out here waiting to be multiplied by whatever comes outside. Let's remind ourselves about rationalizing the denominator. Back when we had imaginaries in the denominator, remember what rationalizing meant? Rationalizing the denominator meant, very simply, making the denominator rational. That's proper form. We must do that. And if we have radicals in the denominator, we must rationalize those as well. So imaginaries and rationals in the denominator are no-nos. We need to convert those. So rationalizing the denominator, again, that's making the denominator rational. And you not only have to do it for imaginaries in the denominator, but you must also do it for your radicals. So here's some layman's terms with the steps that you need to do. So think about the ugly part of the denominator, or the radical part of the denominator. So sometimes it's a square root of 5, or a square root of 2, or a square root of 11. Think about what you can multiply that by to make it pretty. Think about what you can multiply that by to make it pretty. A nice, beautiful number. A rational number. Don't forget that you have to multiply the numerator by the same thing you choose to multiply the denominator by. And don't forget that it's okay for the numerator to be ugly. As long as the denominator is a nice, pretty rational when you're finished, you've done your job. So let's take a look at these practices. First one. The bottom has a radical in it. What can you multiply this by to make it rational? If you were to multiply the square root of 5a times the square root of 5a, you would get 5a. Whatever you do to the bottom, you must do to the top. There's nothing else to simplify, so that's your final answer. So that's kind of the plan that we're going with here. That's for square roots. Now with cube roots, it's a little bit more work. So let's first think about this. The denominator is the only part I care about. So please think of this as the cube root of 5 over the cube root of 2, and only think of that cube root of 2 as the troublemaker, as the problem we need to fix. I don't care that there's a cube root of 5 up here. That's not a problem. It's the fact that there's a radical in the denominator that's a problem. Now, there's a little puzzle we need to solve here. What can I multiply the cube root of 2 by to get something that will result in a perfectly rational number down here? If you multiply it by the cube root of 2, will that get you where you want? If you multiply this by the cube root of 2, you'll end up with the cube root of 4. Is that something that simplifies down to a rational? No, it is not. The cube root of 4 is not cannot simplify down to a rational. So we need to find a different thing that we can multiply this by so that we can simplify this down. I propose to you that if you multiply this by the cube root of 4, you would then turn out the cube root of 8, right? If they're both under the same radical, you can get them here. And we all know that the cube root of 8 is this beautiful rational number of the 2. So that's how we need to solve this puzzle. We need to think, what can I multiply that by so that I get this gorgeous number in the bottom? Whatever I multiply the bottom by, I must also multiply the top by. This now turns into the cube root of 20. I've already done the work on the bottom. There's no perfect cubes sitting as factors within 20. So there's nothing left to simplify there. So the cube root of 20 stays on top. I have rationalized my denominator, so my job is done. Number 3 is an example in don't do more work than you have to. If you think of this as the square root of 8 over the square root of 9, the square root of 9 can immediately be turned into a 3, which is rational. That's fine. There's no more work to be done. There's nothing to multiply that by. So don't do more work than you have to. Do make sure that you simplify completely, though. So take a look at this square root of 8. Is there any perfect square in there? There sure is. There's a 4 times 2 in there. So take that square root of 4, make it a 2, and then leave behind the square root of 2. So do make sure you simplify completely. Number 4. Again, we don't want to cause any more work than we have to. So let's immediately see that we can reduce these. Since these are outside the radical, we can reduce those. We can reduce those down. So we can make this a 3 over a 1. So now I'm looking at the 3 times square root of 2 over the square root of 6. One thing you can do is think, what can I multiply that by? I've got this radical in the denominator here. What can I multiply that by that will fix this? If I multiply this by the square root of 6, that will fix that problem. Because the square root of 6 times the square root of 6 is the square root of 36, which is 6. So that takes care of rationalizing my denominator. Don't forget, whatever I do to the bottom, I must do to the top, so that I don't change the chemical makeup of this thing. I need to multiply it by the number 1 of some kind. So now what happens? I reduce this to a 3, so I've got 3 on the outside, and then square root of 2 times 6 on the inside, or square root of 12 on the inside. Is there any perfect square that I can pull out of the square root of 12? Well, I can think of this 12 as a 2 squared times 3, right? A 4 times 3. And I must simplify. I must pull that 2 out. So let's make this. Remember, this 3 is waiting out here to be multiplied by whatever comes outside. So I must make this 3 times the square root of 2 squared is 2. and then I leave behind the square root of 3. 3 times 2 is 6, and I've got 6 over 6, so I can make this into 1 over 1. So my final fully simplified answer is the square root of 3. That square root of 3 is not on a denominator, so I'm fine. I've rationalized everything. I have no radicals in the denominator, so that's a perfectly fine final answer. Number 5, I've got the cube root of 4 on the bottom that's causing me trouble. I need to solve this puzzle. What can I multiply the cube root of 4 by to get myself a rational number? I need to multiply this by something that will get me to something to the third power. If you think of 4 as 2 to the 2 power, what could I multiply this by to get it to the third power? A 2, right? Or I've got to multiply 4 by 2 so that I can get it into an 8, get the cube root of 8. I've got to get it to something to the third power. If I multiply the cube root of 4 times the cube root of 2, I get myself a cube root of 8. The cube root of 8 is 2. I've rationalized that denominator. Whatever you do to the bottom, you must do to the top. Cube root of 2. 2 times the cube root of 2. 2 times the cube root of 2, check it out, these cancel and leave me with the cube root of 2. Always simplify your fractions as much as possible. If these numbers are sitting out here outside the radical, you can simplify them. And I have no radical in the denominator, so it's completely simplified. Number 6, let's solve the mystery. Now, there's nothing in this 4 to fix, okay? You don't need to do anything to fix this 4. If this 4 was here by itself, he would not be the problem. He would not be the troublemaker, right? The troublemaker is this cube root of 5, so only fix the troublemaker. Only fix the cube root of 5. What can you multiply the cube root of 5 by to get something to the third power that we can simplify? If you were to multiply this by 5 squared, or 25, you will get yourself to the cube root of 125, which is 5, right? And again, I can't stress enough, the faster you memorize those perfect cubes, perfect squares, perfect fourths, the better off you'll be. So let's carry this out. On the top, we've got 3 times the cube root of 50, because the cube root of 2 times the cube root of 25 is the cube root of 50, divided by 4 times the cube root of 125. I can simplify this down. I've got 3 times the cube root of 50. There are no perfect cubes within 50. There's nothing I can find within 50 that's a perfect cube, though I should always look. And then 4 times the cube root of 125 is 5, right? So 4 times 5, that's 20. I can't reduce 3 over 20, so that's my final answer. That's my final simplified answer. Okay? So that's rationalizing the denominator. Again, no radicals in the denominator. That's our goal. Go ahead and try your independent practice.